At the beginning of the year, we learned how to use secant lines to approximate the slope of a tangent line. While secant lines are not perfectly accurate ways of finding the rate of change at an instant on the graph, they are useful for approximating. One other approximation technique used in calculus that can be used to sort of reverse this process is Euler's method. Not those Eulers, this Euler, a mathematician from the 1700s who was immortalized with the E named for him and who solved many other problems in his times. Here he is thinking about his creative solution to the Basel problem.
So, what is Euler's method? Euler's method is used to find solutions to differential equations, and it's useful when integrating or other exact methods of finding the solution are too difficult, or if an exact answer is not necessary. Some equations it may be possible to integrate, but very time-consuming and difficult. Other equations it may be impossible by the means we have learned so far to integrate. Euler's method requires a few prerequisites in order to be applied. First, you need a differential equation. For example, dy dx equals 2x plus 1/2 y. This differential equation may be written in slightly different forms, but it's important to have a rate of change and an x and y or other two variables. You also need to choose or have a step size chosen for you. For example, delta x equals 1. Step size is essentially how much your change in x will be for every increment. This will make more sense when we're using a table of values, but the smaller your delta x is, the more accurate your solutions will be. Finally, Euler's method requires an initial point on your curve. This is where you will start your table and continue your calculations from. It is important to note that while Euler's method is very effective for approximating solutions, it will not give an exact value. I've set up an example problem using the examples I gave above. So we're going to try to approximate f of 4 given that dy dx is equal to 2x plus 1/2 y. Our step size is 1 and our initial point is 0, 2. So I'm going to fill in the initial point 0, 2 for the x and the y. And then this is sort of optional, but you can also put the delta x over here. In this case, the delta x is 1 every single time, so it's not super necessary. But if you're using something trickier, it might be useful. So, first things first, we're going to calculate dy dx based off of these values. So, 2 times 0 plus 1/2 of 2 is equal to 1. So you'll notice that I plugged in the x, I plugged in the y into this equation here, and that got me a dy dx equals 1. So now, imagine we've got a straight line with a rate of change of 1. If x increases by 1, which it does because our step size is 1, then that means y will also increase by 1 because this is our change in y for every change in x. So now we can say 2 plus 1 equals 3. All right, now using these two values, 1 and 3, we're going to do the exact same thing, just repeat it over again. So 2 times 1 plus 1/2 of 3 is equal to 3.5. And once again, we feed it through. So our x is now all the way up to 2 because we just keep counting by 1. In fact, I'm going to fill in the rest of the table. This is our goal, that f of 4 right there. So we're going to bring this 3.5, we're going to add it on to that y. So that gives us 6.5. I didn't write out that, but I think we can understand it's just 3.5 plus 3. And we repeat it. So 2 times 2, that's the x value, plus 1/2 of 6.5 is equal to 7.25. Bring this over. 6.5 plus 7.25, 13.75. So finally, one more time, we're bringing this new y value, this change in y value for change in x, and we're adding on to the x. Adding it onto the y. And the reason we don't need to do anything more complicated with this is because we're counting just by ones with x's. We'll see later that this might be a little bit trickier, but still finding the same general idea. So 13.75, all right, plug that in. So 2 times 3
plus 1/2 13.75 is equal to 12.875, and then we bring the 12.875 over, so 12.875 plus 13.75 gives us our final answer of 26.625. So based off of this, we can say f of 4 is approximately equal to 26.625. And all of this is without even knowing an equation for f of x, just by approximating. We can't say that f of 4 is exactly 6.625, but we can say it's approximately 6.65. I've gone and graphed what this would look like. So I didn't continue all the way up to 26.65 just so you can see the scale better. But you'll see our 0, 1, 2, 3, and it forms sort of like a jaggedy line of these straight connected points. And then this right here is just an approximation of what the actual solution would be. So you can see that the further you go along, the further in the x's you increase, the farther you are from the actual solution. But you're still finding useful approximations. And if you increase the step size, you'll get closer to this. You'll hug that curve a little bit closer. In the second problem, you're not given direction to use Euler's method, but looking at this integral, you may want to use it due to how difficult it would be to integrate. I mean, you see the y prime and you want to get the function at 1.5, and you might think you want to integrate, and maybe you can, but it might also be simpler to use Euler's method and get an approximate since we have multiple choice and they're relatively far apart. So we hopefully will be able to get a clear answer that's not, split in between these. So I've set up the table. This time I included the delta x right away because that is going to be an important decision. So let's put the initial values in. We've got y of 0, so x equals 0, y equals 1, so y equals 1 at the beginning. I'm going to fill in dy dx equals this here. So I used a different notation. We've got a different notation here, but it's still the same general idea. So ln cos x plus ln sin y. Okay, so that's the general form of that. And then choosing a step. We want to get to 1.5, so at some point we're going to have to go by halves. I think, just because I don't want to get stuck in between two numbers, I'm going to count by halves. So delta x is going to be, well, nothing there, but 0.5, 0.5, 0.5. And then I'm just going to fill in the x's now too. Okay, so x's are all set up for the whole problem. Now let's calculate what the dy dx is for each step. So in our first one, we'll have ln cosine of 0 plus ln sine of 1, which is approximately equal to negative 0.1726. It would be a good idea to store more digits of this on your calculator, but just for saving space, writing quickly, I'm going to leave that. And I'm going to keep leaving that in each stage. Okay. So now, that's the change in y for a full step of x. So if we're only changing x by a half, that means we're only changing y by half of this value. Remember how slope would work in this situation, and that might be useful to remember. All right, so y plus half of that value is going to be equal to 0.9137 approximately. Again, I'm not showing a whole lot of digits, but you could be if you wanted to, or just leave them in your calculator. Okay. I'll write out one more full one of these, and then I'm just going to fill in the values. So ln cosine of 0.5, that's coming from the x column, plus ln sine of 0.9137, that's the previous y value, is going to be approximately equal to negative 0.3641. I'm just going to fill in the rest of these values now. So once again, we have to have this because we're only moving a half step at a time. So that gives us 0.7317. All right. We're going to repeat the same process, giving ourselves negative 1.0189. And then our final y, remember to split this in half, would be 0.2222. All right, that is very, very similar to this one, C. So I'm going to say that this is the answer. So despite not having the exact same answer, we know that it's not going to be anything further away from this value because we have an approximate solution. I think this is a great example of how Euler's method can be useful when you're trying to avoid a difficult integration process. Right here is the general equation for performing Euler's method, which I think makes a little bit more sense after having tried Euler's method, which is why I've saved it for now. So the notation can look a bit scary, but it's really the exact same as what we've been doing. So H, I'm going to start right here. H is what I've been calling delta x. It's just the step value. So H is how much x changes by every single time. So if you wanted, we could go back up here and say not delta x, H. But they're really the same thing. This is just another common way. Both ways can be written. All right, then let's take f of x I, comma, y. All right. So a way that this is often given is we have y of y prime is equal to f of x y. So if we look at the substitution here, this is really just dy dx. So that's this column here. So once again, we could be writing f of xi yi. But I think that's a simpler method to remember because it helps you understand the connection between the increments you're changing by and what you're relating with the derivative. Okay. Then let's see, we've got y initial. So this was just our first row. So this right here you could call y initial. And when we're going up each row, we're going to change it. So it could be y1, y2, y3, so on. And then now, this is when we're wanting to go up one row. So if we have y1, we want to get to y2, well, y2 is just y1 plus 1. So that's really just showing that we're counting up as we go. And it tells us how to find any y value we want. Now, a little bit similar to when we did sequences in series, you have to go one step at a time. There's no formula for just jumping all the way ahead within Euler's method, but you can choose your step to be as accurate or approximate as you want
to work your way up to find any approximate solution to a differential equation without needing to integrate. Now go make Euler proud.